Please make sure you have your notebook and a pencil handy, and then you can write down the notes from Chapter 6. The quantum theory has led to the explosion in technological developments in the 20th century, including remarkable new light sources like LEDs and lasers, which have revolutionized so many aspects of our lives. Quantum theory also led to developments of solid-state electronics like computers, cell phones, and countless other electronic devices. In this chapter, we'll explore the quantum theory and its importance in chemistry, and eventually it'll lead to describing the arrangements of electrons and atoms, what we call the electronic structure. If you have a Brown LeMay textbook, you're on page 212. If not, you're more than welcome to follow along as well as we start with the wave nature of light. Much of our present understanding of electronic structure of atoms has come from analysis of the light either emitted or absorbed by substances. To understand electronic structure, therefore, we must first learn more about light. The light we see with our eyes is called visible light. It's a type of electromagnetic radiation. And because electromagnetic radiation carries through space, it is also known as radiant energy. Now, there are many different types of electromagnetic radiation, most of which we cannot see. Things like radio waves, cell signals, infrared or heat we feel from a glowing fireplace, X-rays. All of these travel at the same speed. They travel at what's called the speed of light. The speed of light in a vacuum is approximately 3 times 10 to the 8th meters per second. And all of these different types of electromagnetic radiation, including visible light, travel at this speed. Now, they all travel as waves. They have wave characteristics similar to those like waves that move through water. Water waves are the result of energy imparted to the water, perhaps by dropping a stone or the movement of a boat on water. This energy is expressed as the up and down movements of the water. The same thing with electromagnetic waves. Electromagnetic waves, and waves like water, are expressed by 2 terms. First of all, a wavelength. The wavelength is a different distance from crest to crest, or crest to crest of a wave. The wavelength describes the distance between those crests and is usually measured in meters, centimeters, or nanometers, depending on how large they are. The second item that describes the waves is how many crests pass through a certain distance as they travel at the speed of light. This is called the frequency. And the frequency is measured in how many crests pass in a second. And so it's measured in crests per second, or just per seconds, 1 over seconds. The fancy name for a per second is a hertz, H-E-R-T-Z, like the rental car company, symbolized H-Z right here. Wavelength is symbolized by the Greek letter lambda. Looks like this. Frequency is symbolized by the Greek letter nu, N-U, nu, and it's like a little V-shaped with a little hook on the end. The speed of electromagnetic radiation, 3 times 10 to the 8th, is symbolized by the letter C, like C, except it's the letter C. You can relate all 3 of these in an equation. And all electromagnetic spectra is identified by its frequency and or by its wavelength. You were given a handout that had an electromagnetic spectrum chart, and you can see this area in the middle right here was very small, and that's the visible portion of the spectrum. You can see that wavelength starts at its largest right here in radio waves and decreases as you move to the right. Inversely proportional to that is the frequency, and you can see the frequency is the smallest here at radio waves and the largest over here at gamma rays. More frequent, shorter wavelength, inversely proportional to one another. You can see a color version of this in textbooks or online, and you can see that this one is organized backwards, or the opposite direction of the one I just showed you. where the visible region's still here in the middle, but the longest wavelengths are on this end, whereas the longest wavelengths were over here, and then the shortest wavelengths are down here, with the highest frequency here, but the lowest frequency down here. This gives you a nice color picture, though, of red, orange, yellow, green, blue, indigo, and violet. Electromagnetic radiation has a relationship between lambda and nu. And in table 6.1 in this textbook, it lists some common units for electromagnetic radiation's wavelengths. X-rays usually are on the order of angstroms. Microwaves are in the order of millimeters. Radio waves are in the order of kilometers. And so you can see the length difference and measurements that are usually used for those types of radiation. The relationship between wavelength and frequency is speed of light, or speed of EM radiation, is equal to wavelength times frequency. Or you can put it into a triangle. C is equal to lambda nu. Or if you want to ask your friend what's nu, they'll tell you it's C over lambda. So what's nu? C over lambda. We can do sample exercise 6.2. Sample exercise 6.2 is in this textbook right here, where it says the yellow light given off by a sodium vapor lamp is used for public lighting. It has a wavelength of 589 nanometers. What is the frequency of this radiation? So, as we do with many problems, the first thing you want to do is write down your given, or the information that you know. 589 nanometers is the wavelength, and frequency is the item we don't know. Frequency is equal to C over lambda, or nu is equal to C over lambda, and now we can plug in our values. First of all, 3 times 10 to the 8th for C, and 589 for nanometers. Savvy chemistry students then realize that meters and nanometers won't cancel, so you need to convert from nanometers to meters. 10 to the 9th nanometers in a meter, and you'll notice that nanometers and meters all cancel, and you end up with 1 over seconds, or per seconds, as your units. Numerically, 3 divided by 589 times 10 to the 8th ends up being 5.09 times 10 to the 14th. You can write the units as s to the negative 1 or as hz. Now, if they didn't tell you the type of radiation, that it was a yellow sodium vapor lamp, they could also ask that question after this, and then you would need an electromagnetic spectrum chart, one like you were given in class. And then you could look on this and you could say, oh, here's my frequency. Let's find 5 to the 14th. Looking on frequency, here's 3 times 10 to the 14th. Oh, 5 is really close to it, and you'd see it'd be right in this region here. You wouldn't know exactly what it is, but you could say it'd be in the visible light region. Good luck with your electromagnetic spectrum homework.